Welcome to Chapter 5, Section 3. We're on conservation of energy now. So we're going to do three things today. We're going to identify situations when conservation of mechanical energy is valid, which means we'll talk about what conservation and what mechanical energy is. We're going to look at the forms that conserved energy can take, and we'll solve problems using conservations of mechanical energy. So what is mechanical energy? Well, mechanical energy is simply just the sum of kinetic and potential energies at any time. So we use ME for mechanical energy, and it's just KE plus the sum, that's what this means here, of potential energies. So we add up the gravitational potential energy and the elastic potential energy if they're both present in a situation. So notice, mechanical energy does not include things like nuclear energy, chemical energy, electrical energy, anything like that. It is strictly kinetic and potential energy, as we've already talked about it. Also, mechanical energy is a classification, like a grouping. Okay, it's not a new kind of energy. We're just grouping them together because it makes certain things simpler in physics. So then for us to talk about how mechanical energy is conserved, we've got to look at what this word conserved means. So conserved just means that a quantity will remain constant. So when we say mechanical energy is conserved, it means that if we calculate the mechanical energy at any time for a system, we will always find it to be constant. So whether it's at the beginning or the end, if we add up the kinetic and potential energies, they will always add up to be the same value. However, okay, this is important, mechanical energy is not conserved in the presence of friction. So we're talking about frictionless environments. So let's look at an example of what this means, okay? This means that let's say you are on a diving board, and this guy looks pretty scared, but he wants to jump off. Okay, he's high enough right now that his potential energy is 10 joules, but he's not moving yet, so it has 0 joules. So if you add those two up, right, 10 plus 0 is 10. Now, let's say he's actually jumped off, and now he's fallen down a little bit, so that his potential energy is now 7. Well, because mechanical energy is conserved, his kinetic energy should be 3 now, because that still adds to 10. As he keeps falling down, you'll notice that all of the potential energy is slowly converted to kinetic energy. So here it's 5 and 5, then we get 3 and 7, still adds to 10, and at the bottom it's 0 and 10. So the whole way, they will always add to 10. That's what conservation of mechanical energy means. Potential energy and kinetic energy can both change, but their sum, adding them up, will stay constant. Another classic example of conservation of energy is a pendulum. So this is a pendulum. It's just a ball that will swing back and forth. So this ball is going here and then there. Okay. And when it does that, when it reaches the top of the swing at the highest point, so you remember, potential energy is mgh for gravitational potential energy. So at the highest point, or the most potential energy, it actually stops, right? Because it stops before it can change direction. So its kinetic energy is 0. At the bottom of the swing, it has the lowest potential energy because the height is the smallest. Right, so height here is essentially 0. And then the velocity is the maximum, so it's the fastest it's going. So it'll have all kinetic energy here and no potential energy. And then it will go back up to the same situation we saw on the other side, where velocity is 0, the height is a maximum. So we get maximum potential energy and minimum kinetic energy. And I'm just going to write that here because this is max potential energy and no kinetic energy. And then here we're the opposite. Here V is max, so KE is also max. But potential energy is not anything, so PE equals 0. And then you get back up here, you get max potential energy, and kinetic energy is 0. So it's always just goes back and forth between the two, but the total is constant. So let's look at an example of how we would apply this now to solve problems. So, in math terms, we say that mechanical energy initial equals mechanical energy final. Okay, and we can break that up into its kinetic and potential parts. So we get initial kinetic and initial potential equals final kinetic and final potential. If we then write that all out, and this does take up a bit of space, then we would say 1/2 the mass of the initial velocity squared plus mass times gravity times the initial height will equal 1/2 the mass of the final velocity squared plus mass times gravity times the final height. So we can always use this equation to solve, but sometimes you'll find that it's actually easier just to use these two parts of it. So we're going to do two examples now, showing you how to use it in both of these ways. So this is a classic example of solving using conservation of mechanical energy. What we have here is essentially like a roller coaster for a ball, and we've got its mass up here, 50 kilograms, and the ball is going to roll down. And during this whole time, we'll use conservation of mechanical energy. I've written the equation here. So what we need to do first is find out what it is at this first point. Okay, so at point 1, right, if we find the potential energy, which is mgh, and here, just to make the math go quicker and more simply, I'm going to say that gravity is approximately 10 meters per second squared instead of the 9.8 we usually use, because it'll just be a little easier. So PE here will be 50 times 10, and the height there is at 4 meters, so times 4, so it's 2,000. So if I write that in here for our mechanical energy, this color is kind of hard to see, so let me change to black there. There we go. 2,000. Now, I know that mechanical energy is conserved, so I can write 2,000 all the way across. And that's really my key to solving for it at each place. And I know it's 2,000 because up here the ball is not moving yet. So even though it says down here that the potential energy is 2,000 joules, it's also the mechanical energy because kinetic energy is 0, which also means that the velocity is 0. Now I don't have room on this screen here to solve for all of these, so I'm going to go through some of this pretty quick. But let's take a look at each situation, okay? So we're going to take a look at 3 really fast. For 3, the potential energy is at 0 because it's at the bottom. So then we know that the kinetic energy will have to be 2,000. And then we can solve for velocity by using kinetic energy. So we'll have the kinetic energy equation is 1/2 mv squared. So we'll have 1/2 of 50 times the velocity squared. And if you plug that in your calculator, you will find there that the velocity is 8.9 meters per second. Okay. If we go back to point number 2, we're going to have a mix of potential and kinetic. Okay, so let's find the potential first because we know it's here at 3 meters. So, solving for number 2, we'll use the same equation we did in number 1, mgh. It's going to be 50 times 10 times 3 this time. So we're going to get 1,500 joules. So we can write that here. And now we know 2,000 minus 1,500 is 500. So we're going to have 500 joules of kinetic energy. And then again we can solve it the same way we did that one. So I'll do that down. Let's see here. We'll do it here. So KE equals 1/2 mv squared. Make sure that looks like a 2. So we'll have 500 equals 1/2 of 50 times velocity squared. Plugging that into our calculator and solving, we find that velocity there will be 4.47 meters per second. So we can write that here. Okay. And then the last one is number 4. And in all of them, we've always known what potential energy is because we knew the height. And here we're going to have to solve for the height. So we have the velocity, so this time we have to find kinetic energy first. So solving for kinetic energy, we get 1/2 of our mass, which is 50, times 6 squared. And plugging that in, it ends up being 900. So our kinetic energy here is 900, which means our potential energy is 1100. And now doing our last potential energy, this time we'll have 1100 equals mgh. So 1100 equals 50 times 10 times h. So 1100 divided by 500, the height ends up being 2.2 meters. So I can write that in the last blank here. So this is one example of a way that you can use mechanical energy to solve for the kinetic and potential energies in a system. And you guys will get a chance to practice this in class. Our last now is just a word problem, because I want to show you how to do it with a full equation like you see it written out here, like we wrote it out before. So I already listed the variables, but let's go ahead and read through the problem. So a bird is flying with a speed of 18 meters per second over water when it accidentally drops a 2-kilogram fish. If the bird is flying at a height of 5.4 meters and we ignore air resistance, because remember, it's not conserved in friction, so we're ignoring it, what is the speed of the fish when it hits the water? So the fish has an initial speed of 18 meters per second, a mass of 2 grams. It starts at 5.4 meters, so that should really be H initial. Gravity is 9.81, we're going to use this time, and we're supposed to find the final velocity. So we should be able to just plug everything into our equation here as I've written it out and solve for it. So let's see. We end up with 1/2. The mass is 2. The initial velocity is 18 squared. I'm not going to write units or I'm going to run out of room, but you should be writing those. Then we'll have a mass of 2 times 9.81 times the initial height of 5.4. Plugging in, we've got the mass again, times our final velocity, which is what we're solving for. And then here, the final height, I didn't write it, but the final height is 0. So this whole term becomes 0. So I don't even have to really write it. So now if I simplify this, we've got a lot of 1/2s and 2s, so those cancel out to 1. We end up with VF equals the square root of 18 squared plus 2 times 9.81 times 5.4. And plugging that into my calculator, I get that the final velocity is 20.7 meters per second. So hopefully that is clear and you guys understand it. We'll get plenty of practice in class, and I will see you there. Thanks for listening.